Welcome. My name is Leander Yale from the University of Stavanger, Norway, and I will present my work on the verification of the HotStuff protocol. HotStuff is the consensus algorithm used in the LIBAR or DM blockchain. It is leader-based and has linear communication complexity. Most important for this talk, HotStuff uses a novel model that we call the tree model. In this talk, I will quickly introduce the distributed consensus problem. Then I present the traditional view instance model and the tree model. And finally, I will report on our experience verifying HotStuff, which uses the tree model with IV and TLA PS. In distributed consensus, there's a set of n processes, here shown as hats. The processes append to a shared lock, and some of the processes may fail. Now, in leader-based consensus, there is one process assigned as the leader. The leader proposes new entries for the lock, and the new entries must then be confirmed by 2/3 of the processes, and depending on the algorithm, that may take one or more rounds, and afterwards they're considered as committed and can be added to the lock. If the leader fails, then usually a new leader can retry, and the fundamental problem in leader-based consensus is how to ensure that the old and new leader do not commit different entries at the same index. Many leader-based consensus algorithms use the view instance model. Examples are PBFT and Paxos. HotStuff, on the other hand, uses the tree model. The view instance model uses a matrix of slots. Each slot has a view and an instance. Each view also has an assigned leader that can propose values in a slot in that view, like shown here. Values can get committed, and new leaders can propose values in their views. Committed values are extracted into the lock following their instance. So a value from the first instance goes to the first index and so on. Values can also be committed in multiple slots in the same instance. Therefore, it is important that different views commit the same value in the same instance. This is indeed the main safety property in this model. So no different values committed in one instance. This property can be verified by looking only at a single instance. And this strategy was used in many previous works that first verified safety for a single instance and then extended that for multiple instances. The tree model is different. It uses a sequence of rounds, where rounds are similar to views, as each round has an assigned leader. The tree model also has a root block or genesis block in round 0. The leader of a round can propose a value by adding a new node or block to the tree. Each block has a parent, and this results in tree structure. When a block is committed, the branch leading to that block is added to the lock. If another block is committed, the lock is extended. So what is the safety property in this model? Safety requires that all committed blocks are on the same branch, or equivalent, any two committed blocks are ancestors in the tree. To specify an algorithm in this model, we have to encode the tree structure and specify the ancestor relation. In the rest of this talk, I will tell you how this can be done in IV and TLA PS. IV is a tool for deductive verification of distributed protocols. The main tactic in IV requires the model and an inductive invariant to be specified in a decidable fragment of first-order logic. The main fragment used is the finite almost uninterpreted fragment. Simplifying, this fragment holds relational first-order logic with almost no for all exists quantifier alternations. Ivy can check if a model lies in the fragment, and for models in the fragment, Ivy either produces a proof or a counterexample. If a counterexample is given, then usually that does not mean what you are proving is wrong, but it means that your invariant is not inductive and must be strengthened. I previously said we need to encode the tree and the ancestor relation. So how can that be done in the fragment? To encode the tree, we add a parent relation between blocks. The problem here is that we cannot require that parents exist. Requiring that for all blocks there exists a parent is not in the fragment. Workarounds exist, but they are in my experience not easy to apply. One possibility is to add a relation connecting a block to the round of its parent, as shown here. Requiring that every block has such a round is in the fragment. The reason for this is that the quantifier alternation lies between different sorts, so between blocks and rounds, not just blocks. So let's look at the ancestor relation. Ancestor is the transitive closure of parent. Unfortunately, this cannot be specified in first-order logic. Instead, we add the ancestor relation directly to our model and update it when we add a block to the tree. Generally, the added relations make the model verbose. Also, they probably make it more complex to verify. But generally, it works. So let's look at the TLA proof system. TLA-PS is an interactive prover for TLA plus specifications. TLA plus is very expressive, so encoding the tree was not a problem. Also, we could specify the ancestor relation inductively. However, it was somewhat difficult to work with this definition. I'm not sure if that is a limitation of TLA-PS or of myself, but we went to a different solution. So what we are trying to prove is that two committed blocks are ancestors. So we try to prove that the model, together with some formula phi that says that blocks B and C are committed, implies that B and C are ancestors. Let's assume that ancestor does not appear in the model and phi. Then, since ancestor is the transitive closure of parent, the formula holds if and only if it holds for all transitive relations R that include the parent relation. So it should be possible to prove it only from these facts. The problem is that the ancestor relation appears in the HotStuff algorithm. As a solution, we came up with a simplified variant of the HotStuff algorithm that avoids the ancestor relation, and we proved safety for that simplified version. We believe that our simplified version is not only easier to verify, but also easier to implement, but we have no evidence of that yet. So to conclude, we proved safety of simplified HotStuff in both Ivy and TLA-PS. The proof took approximately the same amount of time for both tools. To give a subjective comparison of the tools, well, TLA-PS is a nice and stable tool. It has an active community which makes it easy to learn. However, the proof requires really many interactions. So you have to write the proof in great detail and only very small steps can be proven automatically. Ivy, on the other hand, is a more experimental tool. I believe it's harder to learn, but it offers more automation and lots of cool features that I did not explore yet, like extraction of source code or verification of liveness properties. With that, thank you for listening. Thank you for listening, and I'm looking forward to take your questions.